Problem 2 is from the 2018 AIME II, and it is problem 3. Find the sum of all positive integers less than 1000 such that the base b integer 36 is a perfect square and the base b integer 27 is a perfect cube. If we interpret this in base 10, well, yeah, 36 is a perfect square and 27 is a perfect cube. So we can immediately say that b equals 10 works. And usually, if you find an observation, it's good to include that, right? Remember that as you go through the problem, because it gets easy to lose track of those more obvious solutions, right? So b equals 10 works. This often happens when you see that like b equals 1 works immediately, but you forget to include it in the final analysis. So we'll write b equals 10 here just to make sure we don't forget in case, we eliminate that case somehow in the future. So let's take a look. 36b is just 3b plus 6, and we know that's a perfect square. Let's look at this equation first. 36 is, of course, 3 times b plus 2, which is true in all bases, right? Because, well, those representations are not unique to base 10. So now we just have 3 times b plus 2. And we know that then, since k squared is a perfect square, k must be a multiple of 3, right? If a prime divides a perfect square, then we know that that prime also divides k. So k is a multiple of 3, right? So let's say k equals 3m for some positive integer m. So then we get that 3 times b plus 2 is equal to 3m all squared, which is 9m squared. So we end up with b equals 3m squared minus 2. So now we can say, let's use that and substitute that into the second equation, which we get 2b plus 7 is a perfect cubed, right? So let's say that's n cubed. Then we get that, well, let's substitute this in. We get 3m squared minus 2 becomes 2 times 3m squared minus 2 plus 7 equals n cubed. 6m cubed minus 4 plus 7 equals n cubed. 6m cubed plus 3 equals n cubed, which once again, on the left, we have a multiple of 3. So that tells us that if n cubed is a multiple of 3, well, if you think about it, that requires n to have a 3 in its prime factorization, right? So 3 divides n as well. So let n equal 3, let's say p, where p is just some positive integer, not a prime necessarily. We just use p because it's basically the next letter. So we get 6 times m cubed plus 3 equals 3p all cubed. We get 2m cubed plus 1 equals 9p cubed. In particular, 9 divides 2m cubed plus 1. At this point, notice that m itself can't be that many numbers, right? In fact, if you look at b, it's 3m squared minus 2. So if b is less than 100, it turns out that, well, 3m squared minus 2 is less than 1,000. Not 100, sorry. So then m squared is less than something like 334. So m is less than like 18 point something, right? Because 18 squared is 324. So we know that m is less than or equal to 18. Also, this is true. At this point, we can sort of brute force our way throughout the rest of the solution, but we can see that this becomes m cubed is congruent to, I think, 4 mod 9. And the only numbers that work now, or I'm writing cubed when I should be writing squares, sorry. So that m squared is 4 mod 9. If we write it like this, it becomes more obvious. We can also just check every single residue mod 9. This can give you more insight, right? So this tells you that m minus 2 times m plus 2 is 0 mod 9. At which point we know that m minus 2 and m plus 2 are two numbers that differ by 4. So they can't both be multiples of 3. So the only possibility then is one of them is a multiple of 9, which because they can't both be multiples of 3. So that means m minus 2 or m plus 2 is a multiple of 9. So we end up with, next page, we get m is plus minus 2, right, mod 9. And remember that we got b equals 3m squared minus 2. So the possibilities, remember that m is bounded between 1 and 18. So m can equal 2. We can be 11 and also -2 or 7. So at this point, we only have 3 different values for b. 10, which we see is the number that we got before, and we know that's correct. For 7, we end up with 3 times 7 squared minus 2, which is something like 49, 145. Or we can have 11, which gives us 363 minus 2, or 361. So let's take a look at 145 first. We know that 36b is going to be a perfect square. Just verify that's going to be 3 times 145 is going to be 435 plus 6 is 441. And then base in 27 would be 2 times that is 290, 297. That is not a perfect cube, so we know that this can't be it. Finally, 361. 36 in base b would be 3 times 361 plus 6, 1089, which is a perfect square, 33 cubed squared. And then finally 27b would be 2 times 361 is 362 plus 7 is 729. Sorry, 722 plus 7 is 729, and that is 9 cubed. So we see that also 361 works. So if we're asking the sum of all positive integers, then we're looking for the answer 10 plus 361, or 371.